Hi there. In this video, I'm going to explain what is an artificial neural network, how it actually works, and thereafter I'm going to demonstrate how to create one in Microsoft Excel. Why Excel? Well, the reality is that many people, working professionals, are not familiar with programming and coding and data science tools like Python. On the other hand, Excel is just accessible. It's used by many people and it's widely available in workplaces and educational institutions. So you don't need specialized software. Excel is also sufficient for solving simple problems with small data sets. So that's why we're actually going to use it in this particular example. So before that, what many people do is that they create a multivariable regression when they have many variables and an output. So we can have 3 variables, and we would have some kind of model, and then we would have some kind of output associated with that model. So let's just say we are modeling the amount of energy consumption in a household. So that's our output variable. And let's just say this depends on these 3 factors. They are x1, that's the number of rooms in a house, and x2 is the number of residents in a house, and x3 is the average temperature in that area. So we would gather this data, we would maybe go to many different households across the country, and then we would survey it and check what's the energy consumption and correlate it or try to correlate it with these different inputs. Many people would build this model and they would use multivariable regression. So a multivariable regression has the form where we have our y equal to, let's just say, w1 x1 plus w2 x2 plus w3 x3 plus an intercept. So very often, perhaps this is not the most appropriate model to develop because we can see that this is a linear regression, and sometimes there may be non-linear interactions between the output variable and the input variable. So we need some kind of model to be able to capture that level of non-linearity. So this is where artificial neural networks are quite valuable and can assist quite considerably. So let's see how an artificial neural network works. We still have our input variables. So we represent things in terms of nodes. So these nodes represent actual data sets. So we have our input variables on the left, and we call that the input layer. And then at the end of the network, we have our output variable, which is what we are trying to get out of this model. And then in artificial neural networks, we have something in between. So we have a series of nodes in between, and this is something that we specify and something that we choose. So in artificial neural networks, we have this input layer, this output layer, and this hidden layer in between. So how the model works is that there is a relationship between the input layer and the hidden layer, and thereafter that a relationship between the hidden layer and the output layer. So let's just say we have our input variables, that's x1, x2, and x3. And then we have our output variable y. So between the input layer and the hidden layer, there will be some kind of transformation between these input variables to each of these nodes. So we represent those relationships as these lines. For example, to x1, to this first node, we would have w11 times x1. So x1 is this data set. So as I said, these nodes represent data sets, column vectors, that's it. So w11 is what we would call a weight. So a weight is just a scalar, and the whole purpose of conducting this exercise would be to determine what these weights are. So the 1 refers to the fact that it's from this first input variable to this first node in the hidden layer. So in the same way, we'll have a w21 times x bar 2, and then we will have a w31 times an x bar 3. So these things would feed into the first node of the hidden layer, and we would call that W1, W with a capital. So this would be its own data set, and it would be a combination or a function of these different relationships that I've just written. So in other words, W1 is equal to W11 times X1 plus W21 times X2 plus W31 times X bar 3. So in the same way, we'll have relationships from all of the nodes in the input layer to each one of the nodes in the hidden layer. So the green lines represent the relationship to the second node, and we'd have another vector W2, and then we would have W3, and then W4, and finally W5. So we can generalize these relationships between the input variables and the hidden layer nodes. So how we would write it is that we would have Wj, where j is the number of nodes in the hidden layer, so here it's 5. And this would equal to just basically the sum of Wij, where I would start from 1 and go up to the number of variables in the input layer. So here I would have the maximum value of 3. So we have Wij times x, each of these input variables. And lastly, at the end, we should also remember that just as we had an intercept with multivariable regression, we also have a bias. So this is b, so it's just a constant that's added to this. So at the end, we'd have plus bj. So we'd have a bias associated with each node like that. So this is the relationship between each of these nodes to the input layer. We now relate all of this to the output layer, and there would be relationships between these vectors in the hidden layer to that of the output layer. So between W1 and Y, the relationship would be Z1 times W1. Similarly, we'll have Z2 times W2, and it will go on like that. So between the output layer and the hidden layer, we'd have our output variable y, and y would equal to Z1 W1 plus Z2 W2 all the way up until Z5 times W5. And if we generalize that, what it would look like is the sum, where we would start from j would equal to 1 and go up to 5, and it would be Zj times Wj, and then we would also have a bias similar to how we had an intercept, and we should also include that here as well. So this Z1, Z2, and so on, these are also weights. So as I said earlier, the whole objective in developing this artificial neural network is to find these weights, W, small letter w, and z. There's just one other thing that we should mention here, and that is, how do we introduce non-linearity inside this model? Remember that the whole purpose of an artificial neural network is to introduce non-linearity. So how does it happen? It happens by transforming this node w by some kind of function. So w1 is not actually the sum as we had written it here. It's actually the function of this sum. So we would compute this wij times x in the way that we had written. Then we would then apply a function to it. We would transform it in some way, and that is actually how we would be bringing out this non-linearity inside this entire artificial neural network. So if we were to now somehow try to write an equation to represent the artificial neural network, what would it look like? Well, it would look something like this. We already have what y is equal to. So all we would need to do is substitute wj inside this equation, and we would have it. So it becomes the sum. This is this outside sum j. And then we have zj. And then we substitute in this function. So we have a function of this sum of wij times our input variables xi plus this bias associated with this hidden layer, so that's bj. And then outside of this, we would have our bias that's between the hidden layer and the output layer. So we should say that this sum is with I. So this is the equation that represents an artificial neural network. And the whole purpose of this is to try and determine these different weights. So in the same way we regressed in the previous section you had seen with the multivariable regression, we had to find the parameters W1, W2, W3, and so on. Here we would go about trying to find these different weights. So a comment on this hidden layer. So with this hidden layer, we can actually have multiple hidden layers. So just as we had this W1, W2, W3, W4, and W5, we would have another one next to it. We could also have multiple output variables, and we can design this network however we want to, but there's different pros and cons with the network configuration that we actually consider. So this is an illustration where we have two input layers. So between W and Z, we would have weights associated with them, and it becomes more complex with the more layers that we have, because that means that we have much more parameters that we have to find to represent the model. So we're now going to see how to create the artificial neural network in Microsoft Excel. We can see we have our data set here. We have our input data set consisting of three variables. They are the number of rooms, the number of residents, the average temperature, and the output variable is the energy consumption. And we are going to build our artificial neural network for this input and output data sets. So the first thing that we're going to do is we're going to standardize the data sets. So why do we do that? We standardize because if you look at these variables, you can see that they measured on different scales. We can see that average temperature has a range of values between maybe 20 and 30. And you can see, on the other hand, the number of residents has a very small range, maybe between 1 and 5, 1 and 6, and so on. So we don't want the magnitude of the actual variables to somehow offset or, dominate the calculations and that sort of thing. So by standardizing these data sets, we actually create a level playing field, so to speak. And also it's beneficial because the algorithms tend to converge faster if this data is converted to be in similar ranges. So to standardize the data set, we require the mean and the standard deviation. So we find just the average for each of the columns. So this would be the average of the first column. And then we can drag that across to find the average for the rest. And then the standard deviation, we just compute that in a similar way. So we do it off the first column, and then we drag that across. So what we're doing is called Z-score normalization. So after we have our mean and standard deviations, we can now proceed to standardize the data. So we're going to do what's called Z normalization. So this is quite a simple thing to do. So the formula that's generally used, we would have X, so that would represent our data set, Xi, so that would be equal to our data point minus the mean of that data column divided by the standard deviation of that column. So if we just put in that formula, so we have our data point, and we subtract from that our mean. So we just put in a dollar sign between the column and the row to keep that value before we move it across. And then we divide by the standard deviation. Again, we put a dollar sign between the column and the row. So we can then bring that downward. And we can also drag it across. So one thing that we just need to mention here as well is that of the validation set. So when we develop our model, we want to test our model. So what we're going to do is we're going to develop our model for about 80% of the data set. So we'll train the model, we'll build the model for this data set that I've just highlighted, and then we'll exclude the last 4 data points as something we're going to use to test. So we'll call that the validation set. So if we look at our standardized data, we can see that they are all now in similar ranges. If we look at our temperature set, we can see that it's not scaled and it's not significantly higher than all of the other variables and will not affect our model in some kind of negative manner. So our next step is to determine the weights. If we go back to our diagram that we had just drawn, we said that these weights W and Z and so on were things that we needed to calculate. So we calculate it through a procedure called back propagation. So how back propagation works is that we guess these values, w and z, and then we proceed to implement the model. We calculate all of these things and get predicted values of this output y, and then we change the values of w. In other words, we optimize it iteratively by minimizing an objective function. So we create this objective function using these output variables y. So in our data set, we have these actual values. So these are the actual values of energy consumption. So we can write that as y actual. So that's actual. And then we have this y here, and this is a predicted values of y. So our objective function is to take the difference between these predicted values and the actual values and square it. And then we're going to minimize this function here by changing these different weights w and z. So we begin by guessing these values for w and z. So we have put them here already. So w represents these different w values here that we have, and z are these values that's in between the input and output layers. And we're going to guess them by assigning them random values. For example, w1j for node 1 actually represents w11. So w21 and w31 is in the same way w21 and w31. So these three cells that are highlighted here represents the weights associated with these three blue lines. So how we're going to guess these values is just by giving it random values. So we're going to say it's random values. So XL will generate values between 0 and 1 with this function. So we're going to multiply this by 2, and then we're going to subtract something like 0.7. So what that does is that it gives us random values between -1 and 1, or typically around them. You can see we have some negative values and some positive values as well. So these are our initial guesses. So we can do the same thing with the z as well. So we just say some random value, we're going to multiply it by 2 and subtract 0.7. And we are going to use these values. So our next step is to now calculate w. So w1. So w1 we saw was w11x1 plus w21x2 plus w31x3 plus this bias. So now we're going to implement this particular equation. We can see that this is w11 times x1, so for that data point, then plus w21 times x2, then plus w3 times x3 plus this bias. So this gives us 0.0666. So this is quite cumbersome to type. So XL actually has a function that can make it quite easier for us, and that's sum product. So we can just highlight these three cells that we're going to multiply, so we can lock those cells because we want to keep it and apply it for all the data points thereafter. And this is being multiplied by x1, x2, and x3. So we just highlight that as per the syntax of the formula. And then we add to that this bias. We're going to say plus this bias, and we're going to lock that. And we can see that we get the same thing. So we then drag this all the way down, and we have W1. So we can just repeat this same calculation for W2, W3, W4, and so on. But there's one more thing that we need to take note of before we proceed. If we go back to our diagram, we said that it's not just this linear combination as we have written it. It's actually a function of it. So what is this function? Well, there's a number of functions that can be applied. So this function is called an activation function. We call that an activation function. So there's two that's commonly used. So one is called rectified linear unit, and another one is called sigmoid. So how do these things work? Well, sigmoid, it's quite straightforward. The function for sigmoid is just f of x is equal to 1 over 1 plus e to the minus x. So if we were to draw it, it looks something like, so let's just go down, we can draw it better. So if we draw the sigmoid function, it looks something like that. So our data takes on this non-linear form. Remember, the whole point of introducing this function is to create a non-linear form that we can work with and somehow put into the neural network. So this is the sigmoid function. So to apply this particular activation function, all we would do is this equation. So for each data point, x, we would substitute this in, and we would find it. So we would do this for each node. So this x is not actually x, it's w. So it's wj. So the other function that I mentioned is this rectified linear unit. So what does that do? So what that does is quite straightforward. So we firstly say that f of x is equal to x if x is more than 0. So in other words, the function is just equal to itself if x is more than 0. However, if it's less than 0, then it's just equal to 0. So in other words, f of x takes on the value 0 if x is less than equal to 0. So if it's less than 0, then the function just has the value 0. So we can just draw that in another color. So how does this create non-linearity in this artificial neural network? Well, it creates it by the fact that at 0, we have a change in the gradient. So this function becomes non-differential at this point, and that is actually how we get this particular non-linearity introduced. So this is actually somewhat, in many different cases, a better function to introduce and to transform our data set by, because it creates a number of zeros in the data set, and that makes our functions or our variables easier to converge in the long run. So let's implement this rectified linear input into our model. So we're going to do that for each of the nodes. So all that's going to happen is wherever we have negative values, they are going to become 0. So we're just going to copy this formula that we already have, and we're going to create an if function. We're going to say that if this value is less than 0, then we want to return the value 0. However, if it's not, then we just want to return the original value. That's why I've copied the formula again. So what should happen is all the negatives should become 0. And when I have put the formula downward, then we can see that actually that has happened. So now we're going to do the same thing for the other nodes. So our data set still remains the same, x1, x2, x3, that doesn't change. However, for node 2, we want to use the weights associated with node 2. So we're just going to refer to those cells. And then we're going to do the same thing with node 3. We're going to drag them to node 3. And then node 4. And finally, node 5. I can just paste this formula downward for this entire data set, and then we can see that we have now determined the hidden layer. So just one other thing to mention here is that we said that we're going to use this as the validation set. So this last 4 points should be taken out of this hidden layer. We're just taking that out. So now that we have our hidden layer W, all that's left is to determine this predicted values, these values of y, and that's just z1 times w1. So we've written it here at the bottom. Y is just z1 times w1 plus z2 times w2, and all of that, and we have to add to that this bias. So these z values have been specified, so all we need to do is just implement that equation. So if we do that, so we're going to take the sum product and we have our weights, Z values, and we're going to lock that, the cells. And we're multiplying that by our W values. And we're adding to that the bias. So if we drag that down, then we have our predicted values of Y. So our actual Y1, we can show that. We can just get that from our data set. So this is the actual values. And we can populate these cells with it. So we must just remember to exclude our validation set. And the square error is just the difference between our predicted and our actual squared. And then we determine it for all our data points. And then here is what we do when we sum the square of our errors. So this SSE, the sum of the square of the errors, is actually our objective function. So this is what we're going to minimize in determining the weights. So now that we have our objective function, we can proceed to actually find these weights through some kind of algorithm. So there are many algorithms that are actually used, and some examples of them are perhaps the method of steepest descent. We also have Newton's method. We also have something called evolutionary algorithms. And each of these have their own way of working and different ways of implementing them. So the one that we're going to use is called generalized reduced gradient. And this is already built into Excel. So it becomes a very simple matter of using this particular algorithm. And it can be used for the data sets of our scale, and it's sometimes quite effective. So where it's built into Excel is through the solver function. So if you go to data, you can see that there is a solver function there, and this can be used to determine these weights. And how we're going to do it is that we're going to vary these cells that I've highlighted by minimizing our objective function, the sum of the square of the errors. So there's just one other thing to note here, and that is sometimes it can happen that our solution that the algorithm will find a local minimum rather than a global minimum. So there's many different solutions, and perhaps you can represent this as maybe something like that, and then that, and then that, and so on. So in this instance here, our global minimum is probably what I will just indicate in red here at the bottom. But it can very often happen that the algorithm will find a local minimum. So maybe one of these that I've just shown here in gray. So it's sometimes very difficult to identify if a solution is a local minimum or a global minimum. And Excel actually has a way of doing that. So we can specify that it can randomize some of these initial guesses that we have chosen, and then it can try and find the global minimum rather than the local minimum. So how we're going to do that is we're going to go to Data, and we're going to click the Solver button, and then Set Objective. So our objective, we're going to specify it as our sum of the square of the errors. So that corresponds to cell R2, so that's indicated there. And then we're going to minimize this. So we're going to click the minimize check. Okay. And by changing cells, so we're going to change our weights. So we're just going to highlight those cells. We're going to highlight those cells. And we're going to highlight the output layer weights as well. So the algorithm will basically change those cells to minimize this objective function. And we should also ensure that this particular checkbox is unticked. So it says make unconstrained variables non-negative. So we don't want to do that. So just make sure this box is not ticked. And then lastly, we are going to use this GRG algorithm that we just spoke about. And we're going to click options. And when we click options, we find that this we find that this dialog box comes up. And in this dialog box, we're going to go to the tab that says DRG nonlinear, and we're going to tick the box that says use multi-start. So this is very important. So this ties back to that local minimum and global minimum and whatnot. So when we tick use multi-start, so what's going to happen is that the algorithm will try and find a global minimum rather than a local minimum. It's not guaranteed that it will find it. Sometimes it may find something that it thinks is the global minimum, but at least it takes some steps to find it. So once we have done all that, we click solve, and we can see that the algorithm is now running. We can see on the lower left-hand side, we can see that it's going through different solutions and it's minimizing the objective cell. So we can see that it successfully found a solution. So it says on the top, after this algorithm has run, is that solver has converged in probability to a global solution. So this is what we like to see. So if we go to our objective function, we can see that it was minimized to 0.0403. And these are now the weights associated with this particular network configuration. If we compare our predicted y values to our actual y values, so we can compare it by just doing a quick plot. We can do a scatter plot. We can just remove the grid lines, and we can put a trend line through this. And we want to look at the R-squared value. So if we compare the actual and the predicted data set, this R-squared value is relatively quite good, and we can see that the predicted values are quite close to the actual values in terms of the model, and we can use different statistical measures, calculate standard error, and so on using this actual and predicted. However, what is important is that we should go back to our validation set. We had said that these last 4 points was the validation set, and we want to test the model using this data set here, because this was completely excluded from the model. So we found the weights, and we did not use the data from that set of values to determine these weights. So it's out of this particular model. It's kind of external. So in validation check, which is this tab here, this is what has been plotted. So these values correspond to the external set, or rather the validation set, the last 4 data points in our original data set. And then we implement the model and we find the predicted. So there's our W values, and then we have our predicted, and we have now the predicted Y values. So when we plot that and we compare it for the external, or rather the validation set that was excluded from the model, we can see that we still get good values, or rather it's relatively quite close to our actual. The predicted is relatively quite close to the actual, and we can actually check that here. So one is actual and one is predicted. So this is the predicted and this is the actual. We just change that to actual. So we have a nice range of values in our validation set, and we can see that if the values were exactly the same, it would correspond to the line y is equal to x. So this tells us that our model relatively approximates, if we try and extrapolate it to external data points, it would give us a good approximation of that. So in this video, we firstly went about explaining how a neural network works, and then we went about taking a data set. We then transformed this data set into Z values, Z normalization, that is, by calculating the mean and standard deviation. And we then standardized it. Then we guessed initial values of these weights. We computed this different values of W and predicted. We went through what's called the feed-forward part of the network. So we calculated the values through the network. And we got our objective function, which was the sum of the square of the errors. We then used the solver function in Excel to change the weights to minimize that objective function. And then we got these weights, and then we compared it to our validation set, and we saw that it correlates generally quite well. In other words, our artificial neural network predicts values that are relatively quite close to our actual measurements. So thank you very much for watching.